Hi, this is a video in which we will discuss conditional probability as it relates to independent or non-independent events. You might remember that two events are independent if the outcome of the first event doesn't alter the probability that the second event will occur. In this section, we're going to explore conditional probability, which is the probability of the second event occurring given that the first one already happened. The format for writing a conditional probability is written like this. Okay, you would read this as the probability of event E given that event F has already happened. The formula for computing a conditional probability is to find the probability of both events occurring together and dividing that by the probability of the first event that occurred. Again, remember, this is read the probability of event E happening given that F has already occurred. So if you're considering the events in time, event F is first and event E is second. It's also important in this formula to ensure that the probability of event F is not 0, so you're not dividing by 0. Another way to look at conditional probability is to understand it as picking outcomes for event E and F from a reduced sample space that contains only event F's, the first event's, outcomes. Let's take a look at an example. Here's a table that shows the results of a survey of 100 stockbrokers. In the columns, we have event E, outcomes, and event not E, outcomes. So event E is that the broker picked stocks that went up in value, and not E is the broker picked stocks that didn't go up in value, or didn't pick stocks that went up. If you take a look at the rows, event F is that the broker used research to pick the stocks, and event not F is the broker didn't use research to pick stocks. Notice we've also put in some total columns. Okay, so you can see the total of the rows here and the total of the columns down here. And what's important is the total of all the totals have to sum up to 100 brokers because that's how many people we surveyed. Okay, let's ask some questions about the table. Okay, take a look at this. This is the probability of event E, okay, that is that the broker picked stocks that went up. If we look at the total in that column, we see 60 out of 100 brokers picked stocks that went up. So there is a 0.6 or 60% chance if we pick a broker at random that the broker picked stocks that went up. Likewise, the probability if we choose a broker at random that he or she didn't pick stocks that went up, there's 40 of those, and so we have 40 over 100 or a 0.4 probability. If you take a look at event F is the probability that the broker used research, and you can see here that we have 30 plus 15 or 45 brokers who used research out of 100 for a probability of 0.45 that we pick someone who used research at random. And likewise, the probability that a broker didn't use research, that's the probability of not F or F complement, there's 30 plus 25 of those, or 55 brokers who didn't use research, for a probability of 0.55. The other thing we want to notice is what is the probability of, if we pick a broker at random, that E and F occurred. That's the probability that the broker picked stocks that went up and that the broker used research. You can see that that is right here, these 30 people. It's where F and E intersect in the table. So we have 30 out of 100 brokers picked stocks that went up and used research for a probability of 0.3 if we were to pick a broker at random. Now let's take a look at some conditional probabilities. Now we've managed to compute all of the probabilities that we're going to need. We want to ask, what's the probability that a broker picks stocks that go up, given that she used research. That's the probability of E given F, which we're defining as the probability of E and F together divided by the probability of F. From our work up here, we can see that the probability of E and F is 0.3, and the probability of F, that's here, is 0.45. When we do that division, we get 2/3, or 0.67. Okay, so there's a 0.67 chance that if the probability that a broker picks stocks that go up, given that the broker used research. Here are some more of similar questions. Find the probability that a broker picks stocks that do not go up, even though, given that, she uses research. The only thing that's different here is our second event is no longer E, picked stocks that went up, it's picked stocks that didn't go up. So we're going to use the not E values here. So we'd have to go back to our table to find out where not E and F intersect. Okay, so that would be not E and F. That's these 15 out of 100 people. So you can see over here I have 0.15 for not E and F. Okay, again, the probability of F, our first event, is still 0.45. So the probability of not E, given that F occurred, is not E and F. Okay, so this is not picking stocks that went up and using research. That's 0.15. And F, again, is the probability of using research. That's 0.45. So here we get 1/3. Okay. This is another type of an example that kind of uses the union rule as well as conditional probability to find a missing piece of a problem. Suppose we're given that the probability of event A occurring is 0.4, the probability of event B occurring is 0.5, the probability of A or B occurring is 0.7, and we're asked, find the probability that A occurs given that B already happened. Well, since we're given the probability of a union and the probability of each event separately, it might make sense to use the union rule for probabilities to figure out whether or not there's any overlap between these events. In other words, are they mutually exclusive? If they aren't mutually exclusive, we can find the probability that A and B occur together, and then we can use that in our conditional probability formula. So let's use the union rule to get the probability of A and B. That's this piece right here. So here's my probability of the union. Here's the probability of event A, and here's the probability of event B. I'm going to use X for the unknown probability of the A and B event. Adding up 0.4 and 5, I get 0.9. Subtracting these 0.9 from both sides gives me negative 0.2 over here and a negative X on the right. Dividing both sides by negative 1 says the probability of A and B occurring together is 0.2, which means, again, they're not mutually exclusive. And now I can use this in my conditional probability formula. Okay, so now I have the probability of A given B. Remember what that looks like. It's the probability of the two events occurring together, so you have the intersection of them in the numerator, and you're going to divide that by the probability of the first event, the one after the given that in the conditional probability. So here I have 0.2, which I calculated from my union rule, and 0.5, which I was given. So there is a probability of 0.4, 40% chance of event A happening given that B already occurred. This conditional probability rule can also be multiplied out to give you the probability of event A and event B happening, given that they're independent events, okay? So suppose I start with this conditional probability formula over here. If I multiply both sides by the probability of event B, you can see that that is going to divide out on the right and leave me just with the probability of A and B. And I'm going to wind up with the probability of B out here in the front of the conditional probability. Here it is rewritten that way. Again, it's important to realize this isn't a brand new formula. This is just the conditional probability formula solved for the probability of A and B. Okay? This formula is useful when the two events are not independent. That is, when the first event changes the sample space for the second one. So the probability of the second event changes. Okay, so in this, the way I have it written here, the probability of A and B occurring is the probability of the first event B, okay, or A, depending on which comes first, and then the probability of the second event. In this case, if B occurs first, then A is my second event. This is the probability of A happening given that B already occurred. If A is my first event, then I have the probability of that first event times the probability of the second event B occurring given that A has already occurred. Here's another example of this. Okay, so let's see if we can figure out the probability of one event and another happening. We have a class that's two-fifths women and 3/5 men. 25% of the women are business majors. We want to find the probability that a student chosen at random from this class is a female business major. So in other words, female and a business major. We're going to call event B, picking a business major. We'll call event W a woman, a female. Okay, and we're given the probability of picking a woman at random is 2/5 or 0.4. What we want to find is the probability of picking someone who is a business major and a woman, a female business major. This is what we have to find. And we're given the probability that 25% of the females, the women, are business majors. That's the probability of being a business major given that you're a woman. Okay, and that's given as 0.25, 25%. So these are the values that are given in the problem. Using the product rule, we have the probability of being a business major and a woman is the probability of being a woman, which was 0.4, 2/5 of the class, times the probability that you're a business major given that you're a woman, 0.25. Multiplying these two together gives us 0.1 or 10% chance. Again, these conditional probabilities are very useful when you have chains of events and you're trying to find the probability of this chain of events actually occurring. Sometimes it's useful to visualize these multiple events with a probability tree. Suppose we are part of a hiring committee and we want to hire a new advertising director. We have two people we're considering, person A and person B. Okay, person A has managed twice as many ad campaigns as person B, and A's ad campaigns are successful 3 out of 4 times, while B's are successful 2 out of 5 times. Suppose the hiring committee randomly selects one of the advertising campaigns, like one of the brochures, managed by A or B, and you want to figure out, well, what's the probability that you selected a successful campaign managed by A, a successful campaign managed by B, an unsuccessful campaign managed by A, an unsuccessful campaign managed by B. Each of these events is going to create a yes or no branch in a probability tree, and each branch has a probability on it. Let's take a look. The first choice, okay, is whether or not we're choosing A or B's campaigns. Remember that we said A managed twice as many campaigns as B. That means two-thirds of the campaigns or the brochures we're looking at are A's, and 1/3 of them are B's. That's why I'm putting the probability 2/3 on the A branch and 1/3 on the B branch. Once we choose a candidate, then we have a choice as to whether the campaign we're looking at is successful or unsuccessful. We were told that 3/4 of A's campaigns are successful, which means 1/4 of them are unsuccessful. Likewise, we were told that 2/5 of B's campaigns were successful, which means 3/5 of B's campaigns are not successful. If we go down each branch in the tree, for example, if we get to this S right here, this is the point where we've picked a campaign that was managed by A and was successful. So we have the probability of A and success. How do we figure out that probability? We multiply the branch probabilities that get us to this point. So I'm going to take 2/3 times 3/4, and that will give me a 1/2. Now what's important to remember is this 3/4 here is a conditional probability. It's the probability of a successful campaign given that A managed it. Likewise, this 1/4 is a conditional probability. It's the probability of an unsuccessful campaign given that A managed it. So to get the probability that I have a campaign by A that's unsuccessful, and realize I could have used not S here as well as U, I'm going to multiply 2/3 times 1/4, and that will get me a 1/6. If I want to find the probability of getting a campaign that was managed by B and was successful, I'm going to go down this branch in the probability tree. So I have a 1/3 chance of choosing a campaign by B, and once I've chosen B, I have a 2/5 chance the campaign I'm looking at is successful, given that it was managed by B. These two fractions multiplied together gives you a 2/15 chance that you have a campaign by B that is also successful. The last branch down the tree gives us the probability of an unsuccessful campaign that's managed by B, or B and not S. That is a 1/3 chance of picking a campaign by B, and a 3/5 chance that it's unsuccessful given that it was managed by B. That gives me a 1/5 probability. So what I've done in each case is I've multiplied the branch probabilities. One thing that's interesting about this is if you add up these fractions, okay, from all of the 4 branches of the probability tree, they will sum to 1. The reason for that is there are no other possible outcomes. So again, if you wanted to know the probability that A runs the campaign and it's successful, you're just going to go down this A and successful branch. Likewise, the same thing with any of the other possibilities. If you were interested in the probability of selecting a campaign that was successful, you have to consider what are the branches in the tree that lead to successful campaigns. Well, that could either be a successful campaign run by A, the probability of that is 1/2, or a successful campaign run by B. That probability is 2/15. And you can see here the probability of a successful campaign is that it was run by A or run by B. Again, these are mutually exclusive because we have 2 different people running the campaigns. So there's a 19 out of 30 chance, which is pretty good. It's more than half of selecting a successful campaign. What we've learned about conditional probability can actually help us define independent events. We can say that events E and F are independent if the probability of event F, given that E happened, is the same as the probability of event F if E didn't happen. Likewise, the probability of event E, given that F has happened, is the same as the probability of E, whether F happened or not. In other words, the outcome of the prior events have no effect on the second event's probability. The way we can state that with the union rule is the probability of E and F occurring, if E and F are independent, is just the product of the probabilities of these two events. What you want to notice here is this second event probability is not conditional because the probability of event F has it's not affected at all by the outcome of event E. Okay, so if you see this type of notation, you know the two events are independent. Let's do an example with this so you can see how checking for independence works. On a typical January day in New York, the probability of snow is about 10%, and the probability of a traffic jam is about 80%. The probability of either of them happening is 82%. So we want to know, are the event it snows and a traffic jam occurs independent? So let's see how we can do that. Again, you might notice this or here is giving us a union of these two events. So let S be the event it snows, and let's let event T be a traffic jam occurs. What we want to determine in order to decide if we have independence is that event T, given that S occurs, is the same as the probability of event T, and the probability of S given that T occurred is the same as the probability of event S. Remember, we said that this was our criterion for independent events. So here's what we know. We know the probability of snow is 10%, the probability of a traffic jam is 80%, and the probability of either of them happening, either or, is 82%. We're going to do what we did before, where we're using the formula for the probability of a union to figure out the probability of S and T occurring together. So here's my probability of a union. I say the probability of snow or a traffic jam is 82%. The probability of snow alone is 10%. The probability of a traffic jam alone is 80%. And I'm using X to represent this unknown probability of a traffic jam and snow occurring together. These two probabilities add up to 0.9. If I subtract 0.9 from both sides, I get negative 0.08 equals negative X, or 0.08 equals X. This is the probability of snow and a traffic jam occurring together. Now let's use our conditional probability. Okay, the probability of a traffic jam given that it snowed is the probability of them both occurring together on top, that's the 0.08, and the probability for snow on the bottom, that's the 0.1. That turns out to be 0.8, which you might remember was the probability of T by itself, a traffic jam. Here's the probability of snow given that a traffic jam occurred. Okay, so I have the probability of the two events occurring together on the top, 0.08, and the probability of the first event, the traffic jam, occurring on the bottom, 0.8. When you divide that out, you get 0.1, which you might remember was the probability of snow by itself. Because we got the same probability, okay, when we tried to do the conditional probabilities, okay, so the probability of a traffic jam given that it snowed is the same as the probability of a traffic jam if it doesn't snow. And likewise, the probability of snow given that there's a traffic jam is the same as the probability of snow by itself. This tells us that the two events are independent. And that's conditional probability.